All right, let's jump right into this explainer. Today, we're taking a look at quite literally the most mysterious, mind-bending objects in our entire universe. Black holes. They've captured the imaginations of stargazers and scientists for decades, and for good reason. We're going to break down exactly what they are, the extreme physics that make them tick, and the completely ingenious ways we actually know they're out there.
I want you to imagine a region in space with a gravitational pull so ridiculously intense that absolutely nothing can escape its grasp, not even light. And you know, light is the absolute cosmic speed limit, zipping along at around 186,000 miles per second. So if light can't even outrun this thing, literally nothing else in the universe stands a chance. It is the ultimate point of no return.
Section 1. Anatomy of a black hole. To really get a handle on how these cosmic beasts work, let's metaphorically drop right into one. At its core, a black hole is exactly what it sounds like. It's a region in space where the force of gravity is just so overpowering that no light escapes. That intense, completely relentless gravity is the baseline for everything we're about to talk about. It's the engine driving all the mystery, warping the very fabric of space and time around it so much that our normal, everyday understanding of physics just starts to break down.
So, zooming in on that outer edge, we hit what's called the event horizon. This is the literal point of no return. Mathematically, it's the exact threshold where the escape velocity surpasses the speed of light itself. If anything, a stray asteroid, a cloud of gas, or even just a beam of starlight crosses this invisible boundary, it is permanently lost to our visible universe. It's a strictly one-way ticket. Actually, if you were to somehow fall toward it, the tidal forces would stretch you out in this terrifying yet kind of fascinating process that astrophysicists officially call spaghettification. Yes, that's the real term. And this absolute, inescapable barrier is exactly why the center just looks like a pitch-black void to us.
Now, assuming we somehow survive the spaghettification and bypass that event horizon, we zoom all the way in to the very center and hit the singularity. This is where things get truly mind-bendingly weird. Any matter that crosses into a black hole collapses into this infinitely small, infinitely dense point. Just think about that for a second. You have the mass of entire stars crushed into a space that essentially takes up zero volume. Zero. At this exact point, space, time, and the fundamental laws of physics as we know them just completely stop working. Our best mathematical models literally fall apart here, leaving us with the ultimate cosmic blind spot.
Section 2. Two types of giants. So we've mapped out the anatomy of a single black hole. But how do these things actually compare to each other out in the wild? Well, first up we have stellar black holes. These guys are born from the massive, violent supernova explosions of dying stars. They pack roughly 10 to 20 times the mass of our own sun into a tiny little area, and there could be tens of millions of them just quietly scattered throughout our Milky Way galaxy alone. But then we have the supermassive black holes. These are the true cosmic leviathans. We are talking millions, sometimes billions of times more massive than our sun. Scientists are actually still fiercely debating how they get so impossibly huge so early on in the universe's history. But what we do know for sure is that they serve as the massive gravitational anchors sitting right at the center of almost every large galaxy out there.
To really put that supermassive scale into perspective, just take a look at this number, 4 million. That is exactly how many suns you would have to squish together to equal the mass of Sagittarius A star. That's the supermassive black hole hanging out right at the center of our very own Milky Way. Not only does it have the mass of 4 million suns, but its diameter stretches about the distance between the Earth and our sun. It's basically the heavyweight champion of our galactic neighborhood, constantly pulling the strings and anchoring the orbit of billions of stars, including our own solar system, in this giant, relentless gravitational dance.
Section 3. Seeing the invisible.
All right, so this brings us to the ultimate paradox of this whole explainer. If black holes are literally invisible to our telescopes because not even light can escape them, how in the world do scientists actually know they're out there? Seriously, how do you study, let alone take pictures of, something completely invisible? It's a massive puzzle, one that frustrated astronomers for decades, eventually forcing them to realize that to find a black hole, you don't look at the darkness itself, you have to look at the light desperately trying to avoid it.
The trick is to look for the absolute chaos they cause in their cosmic neighborhoods. We can't see the black hole, right? But we can absolutely see its immense gravitational effect on nearby matter. For instance, as these huge clouds of gas and dust get pulled toward a black hole, they get compressed and rubbed together at phenomenal speeds. All that friction heats the material to unbelievable temperatures, creating this glowing, swirling ring called an accretion disk. And these disks are so incredibly bright they can outshine entire galaxies. Then we've got quasars. These are unimaginably bright jets of superheated particles that get blasted out from the poles of supermassive black holes at almost the speed of light. So, long story short, we track down the invisible monster by hunting for the blazing cosmic wreckage it leaves in its wake.
Section 4. From Theory to Reality. Let's bring this immense, crazy cosmic phenomenon back down to Earth for a minute and track how humanity actually figured all this out. Because for a really long time, black holes were just a mathematical quirk. They only existed on paper. Back in 1916, a German physicist named Karl Schwarzschild used Albert Einstein's brand new general theory of relativity to crunch some numbers. He calculated that theoretically, if you compressed any mass tightly enough, it would just tear a hole right in space-time. At the time, it was literally just math on a chalkboard. Even Einstein himself was pretty skeptical that these things could exist in the real world. But fast forward a few decades, and the math became reality. In 1971, astronomers studying the constellation Cygnus detected these intense X-rays coming from a mysterious, invisible source that was actively ripping gas away from a nearby star. That was Cygnus X1, humanity's very first physical evidence of a black hole, proving Schwarzschild's wild 1916 calculations stunningly, perfectly correct.
And today? Well, today we know there are just an untold number of black holes scattered all throughout the universe. They're out there right now as we speak, warping space and time, swallowing stars whole, and completely shaping the evolution of entire galaxies. They represent the absolute extremes of our physical universe. So as we wrap up this explainer, I want to leave you with this thought to chew on. As we keep building better telescopes and peering even deeper into the dark, how are these invisible, inescapable forces going to continue challenging everything we thought we knew about physics? And more importantly, how will they continue to inspire our collective imagination?